Hey guys, I hope you all are doing good. In this lecture, we are going to cover time complexity. This is one of the very important topics of data structures and algorithms. This is very important to understand to basically get an idea of how algorithms work, right? And how efficient they are, right? We are talking about efficiency in this case, right? So there are basically two things that we consider when we talk about efficiency of our algorithms, right? So think about this, right? Over the time, you must have noticed that things have gotten so much faster, right? Um, like 5, 10 years ago, it used to take so much time to run applications, like running games or opening a website. But now those times have become very fast, right? You can open a website in like just a few seconds, and game loading times have decreased as well. So how did this happen, right? Very important to understand. So one is obviously the hardware has improved over the time, right? But the second thing is that the algorithms have also gotten faster, right? People discovered better and better algorithms which run faster and are more efficient, right? So what does it mean by efficiency in our case, right? So there are two major things that we consider. One is we consider the time complexity. How much time is an algorithm taking? Think about this, right? This is super important to uh, understand because, for example, loading games or finding some data in some database, right? We need that to happen in a very efficient amount of time or less amount of time, right? So time complexity is basically understanding how much time an algorithm is taking in general, right? So it measures how the runtime of an algorithm grows as the size of the input n increases. So based on the size of the data, we are trying to understand how much time more would it take, right? So like how much does it depend on the input size? That's what we are trying to understand, right? Second thing is, along with time complexity, another thing that is also important is the space complexity, right? How much space is my algorithm taking? How much extra space does it consume? Because think about this, right? We don't have like unlimited amount of memory inside our computers. We need to make sure that we are efficiently using the memory, and we are making sure that we are using it correctly as well. So just a quick summary once again, we need to make sure our algorithms are efficient. And in terms of coding, we consider efficient in two ways. One is that it is time, we consider the time complexity, right? We want to make sure that it takes less time. And second is we consider the space complexity, meaning how much storage does it consume. And again, we want to make sure that it consumes as less space as possible, right? So let's take a deep dive into what is time complexity in this lecture, and then we will understand space complexity in the next one, right? So measures how the runtime of an algorithm grows as the size of input n increases. So this is what we are thinking, right? I'll try to give you an example. Let's say you have a list of IDs and names, right? Let's say you have this big array and it has like 500 different students, right? Let's say you have this database, right? Let's say you have this list or a text file and you store the IDs and names of certain students. There are a total of 500 students over there, right? So I ask you to build an algorithm to find a certain student based on given their ID. So we give the algorithm an ID. Let's say I give the ID 25. The algorithm should find the name of that person, right? Whatever is associated with it. Now, when we are designing the algorithm, right, we need to understand whatever algorithm I've designed, how much time complexity it needs. In this case, we want to understand um, how the runtime of an algorithm will grow as the size of the input n increases. So in this case, n is 500, right? Let's say I create a for loop. Like I check all the values until 25. That's how I can find it, right? So if I increase the size to 1000, how much more time, how much would it affect the time it is taking, right? Like how much it is proportional to the time. This is kind of what we are considering. Right, so as an input increases, how much time is increasing and what's the general case? We're not trying to understand like the exact time more it's taking. We're trying to understand like a general way to get us an idea of how much time would it increase, right? So we consider two types of annotations, right? Two types of time, actual versus the asymptotic time, right? So let's try to understand what this is. Actual time is how many milliseconds it takes depending on the hardware, compilers, and OS. Right? This is just very simple to understand. Let's say you build an algorithm and you're supposed to find the actual time, right? You can start a timer at the beginning of the algorithm run the query and then stop the timer, right? So it's going to give you the exact time that is taking. But here's the part, right? Based on different operating systems, different compilers, the time taken can be different. So maybe the code that I run on my Mac OS would take, like, let's say certain time, let's say 5 milliseconds. In Windows, it might take 10 milliseconds or maybe 6 milliseconds, right? So the thing is that this is not a very general way to understand how much time is it the code or algorithm is taking. We need something of a general way, right, to get an idea of how much time the algorithm might take to run. So in that case, we use the asymptotic time, how the algorithm grows independent of the machine or the language. So in this case, what we do is we're not considering how much time would it take for the compiler, the OS, etc. It's just a very general way to understand how the algorithm will be growing, right? So as the data increases, how much more time would it need, right? So this is just a quick idea for you to understand. We will take a look at examples as well, and it will make a lot more sense. But it's just to give you an idea that we're not considering the actual time. We are considering, like, in general, to give us an idea of how much time would it increase, right? So now let's take a look at few notations for time complexity. Okay. Before we move on to the order of n operations, there's something very important to understand, right? So I've given this example over here. This is to give you an idea of how we measure the time complexity, right? Don't worry too much if you're not able to understand until this point. As soon as we go through the examples, then it will make a lot more sense, right? So let's take a look at this example. So let's say an algorithm performs 3n plus 5 operations for input of size n. When n is huge, these constants don't matter. The dominant term is n. So let's try to understand what I'm saying, right? Look, when we measure time complexity, right, we don't take a look at the small or these constant terms in the case. Why? The reason is, think about this, right? In general, a lot of these algorithms are not just performing on small data sets like 500 or 600, right? Like a data set could be something like 1 million values. A loss of zeros, right? Think about this. How many people are using YouTube right now? How many people have Gmail accounts, right? Those data sets are in billions, right? So that's why when it comes to such big number of operations, right, these constant terms like 3 and 5 over here, they're not going to matter. So we don't say that the time complexity, like when you're asked the time complexity, right? Let's say you measure the number of operations is 3n plus 5. Let's say an algorithm you make and it takes the input of size n and it performs 3n plus 5 number of operations. What do I mean by operations? Operations could be addition, subtraction, multiplication, stuff like that, right? Because you're basically performing some kind of an operation, right? You're probably figuring out whether two values are equal. Maybe you're adding two values, maybe subtracting, dividing values, right? Those are called operations in this sense. So assuming the fact that for an input size n, a database of size n, you're performing 3n plus 5 operations, what happens is when when the input size is very huge, these 3 and 5 are not really going to matter, right? For a very huge data set, 3 and 5 we can just get rid of them in our case. And in general, that's how we measure the time complexity. So in this case, you wouldn't say the time complexity is 3n plus 5. You can say that, but in general, we are just going to remove these values, and the time complexity is simply going to be n, right? So we can say order of n, right? Now, there are different types of notations. We are going to understand them in detail, but I hope this is making sense making sense what's happening, right? We are getting a general idea of, as the input size is increasing, how much more time my code is going to need, right? And another important part is that for very big data sets, we just get rid of these constant operations in our code. Let's take another example, right? Let's say your code takes 4n square plus 6 operations. So let's say you input a size n, right? And it performs 4n square plus 6 operations, right? How do we get this n square in this case? Maybe you have a double for loop, right? Maybe you have a for loop inside a for loop which could double the number of operations, right? Which I should say it would square the number of operations. So let's say this is the number of operations you perform. Once again, what we're going to do is when we are measuring the time complexity, I'm going to remove these constant values. So my time complexity, the answer would be n square in this case, right? We don't really care about the constants, right? We just remove them and we just take care of what is the dominant part, what's actually affecting the growth in our case, right? Now let's take a look at the different types of notations we have. Okay, let's try to understand the big O notation, which is basically called the upper bound, right? What do I mean by upper bound? So it is at most this much time will be taken by my algorithm, right? So what does it mean? So the thing is, based on whatever query we are asking, right, it could be possible that the algorithm takes different times. Let's take a basic example, right? Let's say you have this, again, a database, right? Let's say you have the ID, you store the ID and names. Students, let's say this is, let's say you have 500 different IDs and names, right? Now think about they're sorted in the order of IDs, right? So let's say this is ID 1, 2, 3, and so on until 500. Right? Now let's say that if I'm looking for the ID 1, then my algorithm is just gonna start it and it's gonna find it at the first place, right? So if I'm looking for ID 1, I'm gonna start a for loop and then I'm gonna go inside this algorithm and the first element would be ID 1, right? So how much time did it take? It took me maybe just one operation. But think about in this case, right? Think about in the case where my ID is 500, right? I'm looking for the ID 500 and I start my for loop at ID 1. Then what would happen is the loop would keep going on 1, 2, 3, 4 until 500, right? So it will take all this time. So in one case, it just took one operation, but in the other case, it's taking all 500 operations, right? It's going to find it at the very end. So in this case, in the case of big O of notation, we are finding the worst case, right? The worst time your algorithm can take. And that's what we are trying to measure. So I hope that makes sense with this example, right? So at most this time defines the maximum growth an algorithm can have and shows the algorithm won't take longer than this point. So we need to make sure that this is the maximum as possible, right? Maximum time our algorithm can take. It can take lesser time than that. So for example, in the case I'm looking for ID 3, it's going to take 3 operations, right? But in the case of 500, it's going to take n operations, the exact number of elements we have. Right, so it is possible that it takes lesser time, but we are trying to find the worst possible time it's going to take. So I've given 2 examples in this case, and I want you guys to find the big O for these 2 examples, right? I would suggest you guys to pause the video and try to figure out for these 2 examples. Okay, so I hope you were able to solve this question, and let's try to figure out what's happening, right? So let's try to figure out what is the worst case scenario for this one, right? Or what is the big O of big O for this one? So think about this, right? I start a for loop, right? I hope that makes sense. This is in C code. I hope that you understand that this is just a basic for loop, right? So I start a for loop, and while I is less than equal to n, or I should say less than n, I print the value I. Right? So think about this. How many operations are happening in this case? I should say n number of operations are happening, right? So whatever, in this case, the worst case, the best case, whatever it is, they are both going to be the same, right? The number of operations would always be equal to n number of operations, because I'm printing this value I n times, right? Starting at 0 until I is less than equal to n or less than n. So what is going to be the big O of n? In this case, it would be order of n, right? I hope that makes sense. Why? Because there are n number of operations. Once again, maybe I was performing some other operations in this as well, right? Maybe the number of operations was 2n, but just like I said, right, we just get rid of these constants whenever we measure the time complexity. Why? Because for very big data sets or for very big input size, it doesn't really matter whatever constant is aligned with it, right? We need to take care of the dominant term. That's where we need to focus on, right? Okay, let's take a look at this one, right? So in this one, I hope you guys understand that this is a double for loop, right? And what's happening is I start int I equals 0, I less than n, and then inside this for loop, right, I start another for loop with j equals 0, and then I print both I and j. Right, so I hope that you understand what's happening. It's gonna kind of print all the I and j values, right? But let's try to understand what is going to be the time complexity for this one. Now think about this, right? It has a for loop inside another for loop. So first for this one, it's performing n operations, right? N operations for this for loop, but then inside that we have another for loop, right? So for each operation of this one, we are performing n operations as well. So that means n multiplied by n operations, right? Think about this, right? So I start with I equals 0. So first 0, and then we would print 0, 1, 0, 2, 0, 3 until whatever the value n is. Then it's going to start with 1, I should say 0, 0, 0, 0, 1, 0, 2, and then it's going to start with 1, 0, 1, 1, 1, 2, and then 3, 0, 3, 1, 3, 2. Do you understand what's happening, right? For every single I value, we go through all the j values as well. So which is basically n multiplied by n number of operations. So what would be the time complexity in this case? What would be the worst case scenario? It would be order of n square. Right? Now, once again, we don't care about the constants. Maybe you were doing other operations as well inside these for loops. We need to focus on what is the dominant term. In this case, it's going to be the n square. What does that mean? It means whatever the input size is, the number of operations is square that. Right? In this case, whatever the input size is, the time complexity is the same as that. In this case, in the second example, it is basically the square of that. Right? So I hope that makes sense. Now let's move on to the big O of theta operation. Okay, now let's try to understand the big theta notation, or in other words, we call it the tight bound, right? So now the thing is, just like I said, right, based on what we are doing, it could be that our algorithm needs different amounts of operations, right? So for example, in this case, right, if I was looking for the first element, then it would just take one operation, or I should say the constant time. But in the case that I'm looking for the last value, right, and I start with the first value in a for loop, that would take me n number of operations, right? So worst case would be n, the best case would be just one, right? I hope that is kind of making sense. But we need to also make sure, or kind of get a general idea, right? In general, how much time on average my algorithm is going to take, right? So this is what the big theta representation does, right? It is basically representing the average growth rate, right? So like in general, in average, how many operations is my algorithm taking, right? So it is tight bound, meaning roughly how it behaves in general, right? Now the worst case and the best case scenarios are different, right? Worst case we covered in the last in the previous before this, and the best case would be like in best how best it could perform, right? So in this case it is 1, but we need to also understand in general on average how it's performing. So let's take a look at this example, right? I've given this for loop. I would suggest you guys to pause the video and try to answer this question. Okay, so the answer to this question would be the big theta. We represent it as a O with a dash inside it. It would still be n for this case, right? Because no matter what, right? In this case, we don't really have a worst case or a best case or an average case. They're all basically the same, which is n number of operations, right? You can't do anything because we are still printing all the I values in this case. So it would be theta of n in this case, right? But now let's take a look at this example, right? So let's say I tell you search for name using ID. So let's say my question is search for a name using ID in DA, right? What is the theta, or what is going to be the average growth rate for this one? That's my question. I would like you guys to pause the video and try to figure it out, right? Like how much time on average do you think my search is going to take? So once again, I will have a for loop, right? I'm going to start with 1 and I'm going to 500. I could search any names, but on average, how much operations is it actually taking? So pause the video and try to figure it out. Okay, so let's try to understand this example, right? So I just told you the best case could be that it takes one operation. Just one. Let's say I'm looking for the ID 1, that would be the best case. Worst would be 500 operations. Or I should say 500. I can also say 500, or I can say just n operations, right? That would be the worst. But what is average, right? So if you take the average of 500, right, that would be just 500 divided by 500 divided by 2, and I can say kind of like maybe n by 2 operations. Like, think about this, right? On average, how much would it take? It would be half of this, n by 2. So almost I can say 250 operations for it. So maybe for some time we are searching below 250, for some time we are searching above 250, but on average, that would come down to about 250, right? Or I should say n by 2. But in this case, so I can say theta n by 2. But once again, right, we have this constant in this case, which is n divided by 2. And just like I said, right, we don't care about these constants. Whenever we write these asymptotic notations, we get rid of these constants because we're getting like a general idea. And so in this case, once again, we will remove this notation and we would be left with theta of n. Right? So on average, this is also taking n number of operations. Right? Actually, it is n by 2, I should say, but on average, we get rid of that constant and it gives us the theta of n. Right? Now, let's move on to the big of omega notation. Okay, so the last one is the big O of omega notation, big omega notation, and which is called the lower bound, right? Once again, this is very simple to understand. This tells us the best case, basically the minimum number of operations an algorithm will take, right? So the best case scenario, right? Like in the best case, my algorithm will take this much time, right? Best case, just like I said, let's take a look at an example, right? Let's say the linear search. Let's say, just like in the previous example, we are considering, I want to find a name associated with the ID and I'm doing a linear search, meaning that I start with 1, then I go to 2, 3, 4, 5, 6, 7 until 500. Right? What would be the best case in this scenario? Best case would be I search for ID 1, and when I search for ID 1, right, the first time my loop enters, my for loop enters it, and it checks the condition, it would find out that ID equal 1 and it will give me the name. So how much number of operations is it taking? It will just take one operation, right? So in this case, what would be the best case scenario? It would be theta 1, right? And this is the representation of the big O omega notation. Whenever you see the sign, you should understand that this is basically the best case scenario for a particular algorithm, right? Now, as we move on to sorting algorithms, searching algorithms, we will discuss what are their worst case scenarios, best case scenarios as well, right? But for now, you should have a good idea about what we are talking about, right? So, just like I said, so in linear search, the best case would be that I just search the first ID, so it would be basically 1, and that's pretty much it, right? So in this lecture, we covered the O notation, right? We covered the theta notation and we covered the omega notation as well, right? We covered 3 different notations. This represents the worst case. The O notation represents the worst case, the worst amount of time or operations my algorithm would take. This one represents the average case, like on average, this is the amount of operations my algorithm would need. And this one, the omega, represents the best case, right? In best case scenario, my algorithm will take one operation or this many operations, right? So I hope you guys understand. But in general, we just use the big O notation, which is the worst case scenario, because we want to prepare our algorithms for the worst, right? We want to prepare them for the average and the worst case, right? Think about this. You don't want to prepare an algorithm in the best case scenarios, because that's not going to happen in general. You want to make sure that on average, what is my requirement and what is the worst case that can happen. So we generally look at the worst case scenario and the average case scenario, but in most of the cases, it's just the big O notation. Right, so I hope you were able to understand this lecture, and that's pretty much it for this video. And one more thing, if you guys like my lectures and videos, I really hope that you would subscribe and share it with your friends. And if you have any feedback for me, I would really appreciate that as well.